Let us continue the calculation of coordination number. So, we have calculated packing fraction. Now, we will calculate coordination number. Coordination number. What is coordination number? Coordination number is basically number of the atoms or lattice point from number of the atoms or lattice point which are the nearest to another atoms or lattice point. So, I want to calculate the number of coordination number, means I want to calculate or count the number of nearest neighbor atoms or lattice point of this lattice point or atoms. Okay. So, and nearest neighbor, there are many neighbors, but nearest neighbor of equidistance. So, so if it is the arrangement of these atoms in crystal or lattice points. So, what is the nearest neighbor of this lattice point or atoms? So, immediately I can say these four are nearest neighbor and they have equal distance. Okay. There are other neighbors and they are also equidistant, but their distance are higher than this one. So, that is why not only neighbors, nearest neighbors of equidistance. How many atoms or lattice points are there around this lattice point? So, that is the basically coordination number. So, again it depends on the crystal structure, and mainly we will calculate this coordination number for cubic system. So, for cubic system we have again 3 Brebis lattice, simple cubic, okay, and then other 2 are there. So, let us calculate coordination number for simple cubic system. So, simple cubic, let me draw it. So, this is the simple cubic. So, it has atoms at the corner, only at the corner. Okay. So, if I can consider any lattice point for which I want to know the nearest neighbor or coordination number. So, let us consider this point, this lattice point. So, what is the coordination number of this lattice point? So that's the task we want to do. So here obviously the distance between these two atoms is basically a, these two also a, these two also a. Okay. And so this, let me complete this one, so it will be slightly so one more is there, okay, atom. So except these three, this and this one, other atoms, their distance are different. Next nearest neighbor, if I say, then it will be this along the phase diagonal. So that distance we have seen, that is root 2a, right. And next neighbor or next nearest neighbor will be along the this one, this atoms, this one, this is the along the body diagonal. So that distance will be root 3a. So along the axis, the distance between atoms, two atoms or two lattice point is a. Along the phase diagonal, distance is root 2a, and along the body diagonal, it is root 3 by a. So we can say that this is the smallest distance. So this, with this distance, so we have to find out the how many atoms or lattice points are there at this distance, because we need the number of atoms or lattice point at equidistance. So that number is basically coordination number. So I think you can find out easily. So here immediately I can see this is one nearest neighbor, this is another nearest neighbor, and this is the third one. And from this cubic there is no, these other are not at this distance a, right. So in crystal, this is one unit cell. So this crystal is full of unit cell. Unit cells are arranged periodically in three sides. So it's fill the space. So immediately you can see, if we, so there will be another unit cell, say in this side. Yes, so I can draw it. So this the another unit cell, okay. So so these are the lattice point. So you can see that this distance also a. So from this unit cell, so it will have another nearest neighbor, so that is this one, okay. So, if I so I have, so its nearest neighbor is one can see that it is along the axis. So, along the a axis for this two nearest neighbor, similarly along this axis, so I will have another unit cell below, right. So, I will have another nearest neighbor, okay, and this other axis I will have another nearest neighbor. So, basically if you draw, because this corner, this point is attached with 8 unit cell, that you know, it is attached with 8 unit cell, right. It is attached with 8 unit cell. If I complete this one, so it is like this. Okay. So, these two and these two, these are the nearest neighbor in simple cubic crystal. When you will draw this 8 unit cell attached with this, so you will find that this only these 6 are the nearest one having the distance a. So, in case of simple cubic crystal, we will tell that the coordination number is 6. Similarly, you can calculate for BCC, body centered cubic crystal. So, what is the coordination number of this? One has to find out. So, again, so I think now easily we can tell this for BCC. The smallest distance was √3/2, √3a/2, that during calculation of radius we have seen. Okay. So, if I consider again this point, this lattice point, then what will be the coordination number for body centered cubic crystal. So, I can put this is the body diagonal. So, at the center of this there will be atom, right, and this distance is √3a/2, right. So, this distance is √3a, so this distance will be √3a/2. Okay. So, these are the nearest distance, and other atomic distance, next one, this distance will be a. So, in body centered cubic, all distance, this earlier this we have seen the distance are a. Now, we are getting, in case of BCC, we are getting even one lattice point that is sitting is at the body center. So, that distance is smaller than this one. So, for BCC we have to find out the how many lattice points or atoms are there at distance √3a/2, that we have to find out. So that same way one can proceed. So this one, this corner point, this whatever we have considered, second this one is attached with the, this point is attached with the 8 cube. So this is 2, and on top this side 2, right, and in again bottom we will have this, whatever top 4 and bottom will have 4. So 8 unit cell attached with this one. Okay. So 8 unit cell will have 8 unit cell. We have this is the body diagonal of this unit cell, I think so, yes. So here this body centered atoms are there. Here I think I think this is the body center. So distance of this between the body centered and this lattice point, this is a root 3 a by 2. So this is 1, you will get the another one 2, and this side again will get the 2 more unit cells are there. So we will get this is third one, and this will get the fourth one, right. If I go down, so this is the fifth one, this side if I draw, so there will be the sixth one, right, and 2 more are there, this below of this one. So we will have 7th one and 8th one. So 8 unit cell attached with this one, each unit cell have the body centered one, and the distance of all these 8 body centered atoms from this point is same. So they are equidistant, and smallest distance, equidistance as smallest distance, and that distance is this root 3 a by 2. So this is the 8 number of nearest neighbors in case of BCC lattice, and thus the coordination number is 8, right. So this way one can calculate for FCC lattice. This also is it's similar way we can proceed and find out, right. So what is the coordination number for FCC lattice? So let us use the same figure in case of FCC. So this in case of FCC, the additional lattice point at each face, at the middle of each face. So this each cubic has 6 face. So we will have 6 so this face here, this one I can use probably okay. And then so I have many more, this one and this face, so it will be middle of this, right, and this one at the center of this one. So 1 2 3 4 5 6. So for this unit cell 6 faces are there, so we'll get 6 6 atoms or lattice point at the center of each face. So obviously if you see this from this lattice point, what will be the nearest neighbors? So that one has to find out first. So again we have seen this the smallest distance between, so this along the face diagonal. So this distance is basically root 2a. So here if we see this root 2a, this distance. So now in middle one atom are there, okay. So distance will be half of it, so it is root 2a by 2, right. So now let us find out how many numbers are there at this distance root 2a by 2. So that's the task we have to complete. So for I think so these faces attached with these corners, that atoms on that face will be the at this distance, but atoms on other faces will be having the higher distance. So I will just remove these points for, so then picture will be clear, I think, yeah. So this is one face attached with this this point, okay. This is another face, this is another face attached with this one, this is another face attached with this one, right. So here, and this is the third face, okay, attached with this point, okay. So from this unit cell there are 3 nearest neighbors having the equidistance of this one root 2a by 2, right. So similarly from other unit cell, so we have 8 unit cell, so from each unit cell 3 faces will be attached with this one. So 3 face will have 3 face centered atoms or lattice point. So here just we can see, so this face is attached for this unit cell, so this face is common, so it is attached with this, and then I can see this face is attached with this, so we will have in this case say here, okay, and I have to complete it. Then this face is attached with this one, so I will have another face centered atoms, okay. So again from this unit cell, so So these three are attached with these three atoms, they are having the same distance. So again from here we are getting 3 nearest neighbor, right. So but one thing you can observe that, as you know, in case of face centered lattice point per unit cell, when we calculated, then we considered that it is 4. Why? Now each face shared with the 2 unit cell, right. So that's why what we have considered there. So this we have taken the contribution half to this unit cell. So 6 faces half contribution, 6 faces half contribution. Okay. So thus basically for that unit cell it was 6 into half equal to 3, right. And from corner point, 8 corner point is shared with 8 unit cells. So it's 1/8 from each corner. So it was 1. So 3 plus 1. So that was is 4. 4 lattice point per unit cell. Okay. So from there we have learned that each phase shared with 2 unit cell. So when here we are seeing that nearest neighbor are 3, from each unit cell nearest neighbor are 3, from each unit cell nearest neighbor are 3. So I have, so this is attached with the 8 unit cell, this is attached with the 8 unit cell, right. And from each unit cell 3 are, from each unit cell 3 are the nearest neighbors, right. And again this each one, this out of these 3, each one is shared by 2 unit cell, is shared by 2 unit cell. Okay. So basically for, so contribution is half, contribution is half for 1 unit cell. So 3 from each unit cell, but these 3 are not fully from this, it's these 3 are shared with other unit cell. So basically per unit cell these 3, so contribution will be 3/2, half of it, okay, because these 3 are shared, each one is shared by the another one. So 3/2, okay. So how many nearest neighbor then? The nearest neighbor from here you can see this is 12, okay. So thus the coordination number for FCC, that is 12. So this way one can calculate the nearest neighbor. This is the first nearest neighbor. If you say, then if I ask you to calculate the, what is the coordination number of second nearest neighbor, what is the, I do not know whether we should call coordination number. Coordination number generally indicates the smallest distance, nearest neighbors are situated at the smallest distance. But for cubicity, if you want to find out the how many numbers are there for next nearest neighbor. So take as a homework, calculate the second nearest neighbor, number of second nearest neighbor, for cubic system. that homework you can do yourself. And this not for only cubic system, one can calculate for other cubic system, other crystal system. So you have orthorhombic crystal, hexagonal, tetragonal. So for other cases one can calculate, and I think you should practice for learning the things, and more you practice, more you learn, and concept will be clear, because geometry is involved in crystallography. So if you do more homework, your concept will be I think more clear. So I will stop here today. We will continue the other aspect of the crystallography, crystal structure. So in next class we will start this crystal planes and how it is identified. So generally we use Miller indices. So I will talk about that, crystal planes and Miller indices, in next class. Thank you very much for your attention.